So I am Edward Sciberras from the School of Electrical and Electronic Engineering at Newcastle University, and I've been involved in INOMANS2HIP on the energy management system side of things. So my work involved creating this algorithm using Particle Swarm Optimisation to implement an energy management system for the new power system on board the ship. So we used an algorithm called the Particle Swarm Optimisation. This is a really interesting algorithm which is inspired by nature, and it takes its inspiration from a flock of birds. So the idea is that each individual particle, or bird in that case, is individually dumb but collectively smart. And if you create a computer algorithm to mimic that behavior, together they can explore a search space efficiently and then zoom in towards your global optimum. In our case, that is the minimization of fuel consumption. In the case of the original birds, that goal is finding food. So, when applied to the new power system on board the ship, we realized savings of about 12 to 13%. That is compared to the previous conventional system on the ship. So the savings are coming about both from the power network, from the new power system, as well as from our optimization algorithm, which optimizes the set points of each of the components in the new system. Now, the big advantage of this is that our algorithm is very generic and standalone. So the idea is that it takes a black box approach, and so it's very independent from the actual system to be optimized. The good thing behind that is that it can be very easily scaled or applied to something else. So if the ship has a new network, by simply changing the variables and changing the constraints, the EMS can be applied to the new system. So on the demonstrator, the EMS is going to be implemented in a real-time case. There is a existing HES and hardware-in-the-loop installation, which will emulate a real ship, and our EMS will integrate with that hardware and pretend that that is our ship, if you like. So it will be running continuously in pseudo real-time, taking inputs from this ship emulator. From there, optimizes the configuration, returns the optimal set points, both the ship emulator as well as the HMI, that is for display and for as well as for a kind of implementing the set points, and then that process is repeated continuously until the journey is finished. So after implementation on the demonstrator, we've got other ideas about where we can go with this work. One of the good ideas we have is taking it a step further and using some kind of self-learning algorithm. It learns from previous voyages and can infer what's the probability of an event happening in the next half an hour, for example. So that is especially based on ships which do a very predictable profile. So based on previous experience, and for example coupling weather patterns as well as the time of the voyage, it can infer what the likely power demand and what the likely, for example, configuration needs to be in the next half hour. And the result of that is that it can optimize not just for the now, but also considering the then, making it a more of a holistic voyage profile optimizer. So energy management is quite a hot topic at the moment. With new ship configurations, you get more integrated systems where your power system, both propulsion and auxiliary, are very much integrated. But that of course brings additional complexity. Especially this comes about when the batteries are involved in energy storage. So we get fuel cells or other sources of power. How to best manage the optimum configuration, if you like, is quite a complex thing. The good thing about an EMS which uses an algorithm like the PSO is that it's very black box, so it can be very easily applied from one application to another without requiring too much detail about what the actual problem at hand is. So I expect we'll be seeing more algorithms which take a similar approach, perhaps in the not too distant future.